Hello, this video is going to focus on the stereochemistry and regiochemistry for the substitution and elimination reactions. So let us start with the E2 regioselectivity. How do you determine if an E2 reaction is regioselective? First of all, we need to think of the conditions for E2 reaction. An E2 reaction requires a strong base. The reaction takes place in one step, which involves a concerted mechanism. So, if we use a strong base, there are two possibilities. We could remove a proton from there, or we could remove a proton from that position. So when there are two different beta sites to remove a proton from, then we can end up forming different products. So one of the protons is in a hindered position. So we can say that this position is less accessible. The other proton is exposed because it is in the periphery, so it is easily accessible. If we remove a proton from the less accessible position, so if we use this base to remove that proton, the electrons go there and we remove the leaving group, so we end up forming a more stable alkene, the one that's more substituted. In this case, we're going to call it a Z-safe product. If we remove a proton that is exposed, so we use a base to remove that proton and we end up with the product which is going to be less substituted. We call that a Hofmann product. Okay, so we can actually choose an appropriate strong base so that we can determine which side of the product is going to be favored, whether we're going to favor a Z-safe product or the Hofmann product. The way we do that is we can choose a base that is less bulky. The less bulky base is going to be able to remove the less accessible proton because it is able to find its way to the hidden proton and remove it. So that will favor the formation of the Z-safe product. If you want to favor the formation of the Hofmann product, then we can use a sterically hindered base, which is bulky. So when you use a bulky base, this bulky base will only access the proton which is exposed. And when it accesses the proton which is exposed, it's going to lead to the formation of the less stable alkene. How do you determine if an E2 reaction is stereoselective? So because we are doing E2, we are going to be using a strong base. So there are two positions where the protons are located, so we can remove any of them. So when we have identical protons in the beta positions that we can remove, then the difference is going to be on the stability based on either the E product, that's the E alkene, or the Z alkene. Z in the sense that the high priority groups are on the same side, E in the sense that the high priority groups are on the opposite sides. So we end up forming an E product as the major because the E product is more stable than the Z. Why does the reaction shown below only form one product? So here we're going to consider what is called stereospecificity. In stereospecificity, the proton to be removed must be anti-coplanar to the leaving group. So in other words, they have to be on the opposite sides of the same plane. If one is on the bottom, another one should be on top on the same plane. So what happens is that we can draw a Newman projection for this compound. When we draw a Newman projection, then we can look at the Newman projection from here. So look at it at this angle, assuming you are at this position. This is where your eye is, and you're focusing on that carbon-carbon single bond. The phenyl group here, the pH, is going to be on your right. The methyl group is going to be on your left. When we look at the front carbon, the hydrogen is going to be on the plane. If we look at the carbon at the back, the one that we show using a circle, the one at the back, the bromine is on the plane. We have the hydrogen being on your right. So the hydrogen is over there on your right because it is coming out of the board towards you. The tert-butyl group is on your left because it is behind the screen. So we have it over here, and then the bromine is going to be on the plane. So when you look at the anti-coplanar, the bromine and the hydrogen are on the same plane. One of them is up, another one is down. So this kind of arrangement allows for elimination to take place. So if we have a base, the base is going to remove that proton, the electrons go there, and we kick out the leaving group. So the arrangement here is important. Those four atoms need to be on the same plane. Let us look at this example. Explain why the molecule on the right is not able to undergo E2 elimination. The one on the left, if we start with that, we can see here we have the chlorine is on the same plane with that hydrogen, so we cannot use that hydrogen to do elimination. But we can use the hydrogen, the one behind the screen, to do elimination with the chlorine because they seem to be on the same plane, but they are on the opposite sides of the same plane. So we can be able to do elimination. When we look at the one on the right, there is no hydrogen that is on a different side with the chlorine but on the same plane. So what we see is that all the hydrogens lie on the same plane but not anti. So all the alpha protons are on the same side with chlorine. So that means there's going to be no elimination. In a chair conformation, the halides strongly prefer to eliminate in the axial position. Why is that so? Now, we recommended before that when you have a bulky group, it needs to be in the equatorial position. So this is the preferred position for the compound to be stable. However, when it wants to undergo elimination, then it has to acquire an orientation that will allow it to have an anti-coplanar so that we can have the arrangement of the proton and the leaving group being on the same plane. So we can do that if we draw the molecule in such a way that we are able to visualize that orientation. And when we do it, it happens that the axial position of the halide is going to be the one that is being favored during the elimination process. Moving to the E1 reactions, predict the major organic product for this reaction here. So in this case, we are using a weak nucleophile and a weak base. So this tertiary alkyl halide will undergo a transformation to form a carbocation first. So we're going to end up with a tertiary carbocation after we kick out the leaving group. And then we can have the proton being removed from either here or any of these two positions that are similar. So we can remove it from here or here. That will, one of them, if we remove it from the one that is sterically hindered, we are going to end up forming the more substituted alkene. If we remove it from this position or this position, we are going to end up forming the less stable alkene. We can also use the water as a nucleophile to form the SN1 product. So we form both SN1 and E1 products. So because we have two positions, so this position and that position are different, so we say that this reaction is regioselective. We have two beta protons that could be removed to result into different products. How about this other example? So here we're going to have 1, 2, 3, 4. So we have a tertiary carbocation. So in this case again we have water, but then there are similar protons that can be removed. So when there are similar protons that can be removed, then the difference is going to be in the stereoselectivity. So in other words, we end up forming either E or Z alkene. So what happens is, if we remove this proton, we are going to form similar product just like when we remove the next one. So the only thing is that one of them might be where the bulky groups are on opposite sides, so that forms an E alkene. Or we might have the bulky groups being on the same side, so that forms a Z configuration. Z for same side. Explain why a chiral alpha carbon undergoes SN1 reaction to form two substitution products that have opposite configurations. So we are told that we are using a chiral alpha carbon. Chiral in the sense that it's attached to 4 different groups. So we have a stereo center. So what happens in this case is that it is an SN1. And what do you know about SN1? It involves the use of a weak nucleophile. A weak nucleophile is going to wait until we form a carbocation. So here we form a tertiary carbocation. The formation of the carbocation is the rate determining step because it is the slow step. Okay? Once it is formed, then the nucleophile can attack either from the front or it can attack from the back side. Okay? When it attacks from the back side, we end up with one product. When it attacks from the front side, we end up with another product. And what you can see is there is inversion of configuration. So we end up with a mixture. One leads to retention of configuration, another one leads to the inversion of configuration. So typically we would expect the yields to be 50%, 50%. However, the one that attacks from the back side is slightly greater than 50%. Now, we know that in the transition state, when the leaving group is being kicked out, there is still some ionic interaction. Okay, so if the nucleophile is attacking from the front, there is going to be some steric hindrance because the leaving group is still going to be lingering closer to the carbocation. So the yield for the one that attacks from the back is going to be higher than the yield for the one that attacks from the front.